All right, so hopefully the angle's not too bad, and this will suffice for going over the Module 2 practice problems. I left my document camera at school, so we are restricted to the iPhone. But nonetheless, before we begin, let's make sure we recall there are three main kinematic equations, and of course the simpler one from Module 1 that we used quite a bit. Distance is equal to average velocity times time. Again, that is interchangeable with displacement, okay? But whenever, the direction doesn't change, we can just use D. So you wanna be familiar with these, but I wanna also give you a little bit of comfort. You're going to be given these in class on your test. So go ahead and get started with the first one. And I did paraphrase here. An athlete at constant velocity of 3 meters per second. How far will they run in 25 minutes? So what we're gonna first do is convert 25 minutes to seconds. So we just multiply by 60 seconds in 1 minute. And so I left my calculator, there it is. We get our calculator out. Hey, you can even fit that in the frame, right? So the minutes will cancel. 1,500, yeah, you can sort of see that. So we have 1,500 seconds. Well, why do we have to do that? Well, our velocity rate is meters per second and our time is in minutes. So we've got to change one or the other. I figured it'd be a lot easier to change 25 minutes to seconds, but you might disagree and think, well, we could just say that's 120 meters per minute. So either way, right, if we say that that's 120 meters, 180 meters per minute, that's that one you see every day. Then we know we're just gonna multiply that by 25, right? D equals 25, that's our time, times our velocity, which is constant, so the average would be the same there. 25 times 180, I'm getting 4,500 meters, right? But what if we had used this 1,500 seconds, right? So again, remember, I'm just doing D equals average velocity times time. Average velocity would be equal to the constant velocity in this problem. So if we keep the 3 meters per second rating here, and then the time we change to 1,500 seconds, then you can see how the seconds will cancel, and 3 times 1,500 is, of course, the same answer, 4,500 meters. Okay, a BMW accelerates 0 to 60 miles an hour in 7.9 seconds. What is the acceleration rating? So what we've got to do is convert. Similar idea here from the last problem. We had to have a consistent time measurement unit. So we've either got to convert everything to seconds or hours. Let's see, I think I'm going to change miles per hour to miles per second, and then maybe we can go back. We've just got to find the right answer depending on whatever units we want. I don't think the problem's specified. So, yeah, let's do that. 60 miles per hour times, let's do it this way. Miles an hour there. And then we're going to, let's see, how many seconds? We know that they're in 1 hour, there are 3,600 seconds. And so what we get here, let's see, that's gonna go 1 over there. And so we get 6 over 360. Well, that again will be 1 over 60. 1/60th of a mile per second. 1/60th of a mile per second. So what we've just done, 1/60th miles per second, I should say, is found 60 miles per hour in miles per second. All right? Okay, well, that makes sense because 60 miles per hour actually equals 1 mile per minute. And then you divide by 60 again, 1/60th of a mile per second. You guys probably don't do that in the car, do you? All right, anyways, now that we have our velocity, our final velocity, right, because this is final velocity, our initial velocity was VI. Well, why do we need to mention that? Well, they're looking for acceleration. And acceleration is defined as the change in velocity over the change in time. So we know the change in velocity goes from 0 to 1/60th. So that's going to be 1/60th miles per second And that took how long? 7.9 seconds. So if we do that simple division, all right, 1/60th divided by 7.9, slide my calculator in here. So we'll do that 1 divided by 60, and then we'll divide that by 7.9. And it doesn't give us a really nice number, 1/474. So we'll go ahead and just use this really nasty repeating decimal. 0.0021 miles per second squared. All right. Weird units. I know, but that's one way to do it. Of course, you could do that in miles per hour squared, and you get a significantly larger number. What you'd have to do is multiply by 3,600 to the second power. So we'll stick with this one now. We don't want to do it too many times. How far does the BMW in number 2 travel? So what we want to make sure we do is go back and review our kinematic equations, right? Pause the video if you didn't write those down, write them down. And then we got to pick the one we want to use. Now it's asking for displacement. So you realize that appears in 2 different ones, but they both require acceleration. Only one of them requires time. And so we're actually kind of opened up completely here, but what we're able to do, as long as we convert, as long as we convert our units, we're able to use either one. So I'm going to use this one. So I've got VF squared equals VI squared plus 2A delta X. Remember, the BMW started from rest, so that goes away. The final velocity is 60 miles per hour. But wait a minute, I changed that to 1/60th of a mile per second. Now, make sure you don't do this. Don't put in 60 miles per hour here and then your acceleration in miles per second squared. It's not gonna match up. We need our units to be consistent. So I've got 1/60th miles per second squared. That's gonna equal 2 times A, which is this value, again, consistent with miles per second squared, 0.0021. And then delta X is the unknown. So we've got a little algebra here. Remember, this is going to turn into 1/3600. And this will, of course, just be 0.0042 times delta X. So what we'll do, we'll divide both sides by 0.0042. And we'll see what we get. It may help if you want to change 1 divided by 3,600 to a decimal. Let's see, let's divide that by 0.0042. 0.066. Okay, so we have delta X equals 0.067. But wait a minute, what are the units here? So remember, we had miles per second and miles per second squared here. So this will, of course, have to be miles. If you wanted to change it to feet, you could do that. That would maybe a little bit easier for us to think about. But this is less than 1/10 of a mile. That's pretty fast. All right, moving on. So number 4, more car problems. A car at 25 meters per second stops in 0.103 kilometers. Find the deceleration value, right? We say it's acceleration, it's just going to be negative. So it might help for us to go ahead and say, since this is 25 meters per second, we can make 0.103 kilometers 103 meters. Remember, because we can move the decimal 3 times if we're going to go to a smaller unit. King Henry died by drinking chocolate milk. So what just happened? We went from kilo to the base unit of meters. So I went 1, 2, 3 to the right, 1, 2, 3. You guys remember that, right? So 103 meters, initially traveling 25 meters per second. So we're gonna start writing down the information given. VI is 25 meters per second. VF is, of course, 0 because it stops. And then we have delta X, which is 103 meters. So if you think about that, that closely relates to which kinematic formula? This one. Again, we've got VF, VI, and A. It makes sense. We don't need time in this problem. So I'll write my formula. You guys have probably noticed I do that every time. I don't just go ahead and plug in. That's just kind of a habit. So we have 0 equals 625 plus 2a times 103. So hopefully you guys will be able to see that if this positive number plus this value adds together to get 0, then I'm going to have to get a negative product right there. Okay, so I've got negative 625 equals 206a, and so we'll divide by 206, and that's going to give us our value. So type it in, 625 divided by 206. Why didn't I put the negatives? Well, I know it's going to be negative. Just be careful there. So a negative 3.03 meters per second squared. So make sure we use the correct units for an acceleration value. Okay, a rocket accelerates from rest to a distance of 2,000 yards. So I wrote it kind of funny. It reads better in your book. A rocket covers 2,000 yards as it accelerates from rest at a rate of 9.7 times 10 to the fourth feet per second squared. So what is the final velocity? All right, how fast would it end up going if it had 2,000 yards to accelerate? So the first thing I hope you notice is that the displacement's in yards, the acceleration's in feet per second squared. We're gonna have to change one of those. I think it's gonna be easiest to change the single quantity, 2,000 yards to 6,000 feet. So we'll go ahead and take note of that, 6,000 feet. Okay, the next thing we're gonna write down, yep, it accelerates at 9.7 times 10 to the fourth. If you wanna go ahead and change that to 9.7 and then 3 more zeros, that would be okay too. Feet per second squared, that is really fast. Oh yeah, it's a rocket, okay? And of course, we also know that VI is equal to 0. Why? Because it started out at rest. So VF squared equals VI squared plus 2A delta X. Again, we've kind of been using that one a lot the last couple problems. So we don't know what VF squared is, but we do know that VI squared is 0. Our acceleration is 97,000. And then our displacement is 6,000 feet. So again, the units of my velocity I should get are feet per second. We want to get that in feet per second. So, of course, before we go any further, let me make sure you realize this is VF squared. So in order to get what VF is, I'm going to have to take the square root of both sides, right? So we'll just go ahead and type that in that way to save time. 2 times 97,000 times 6,000. And so we're going to get 34,117.4. That's a lot of sig figs, right? 1, 2, 3, 4, 5, 6. Too many. Feet per second. So this thing is scorching. With an acceleration rate like that, of course it is. Okay. What about Carowinds? A free fall rod drops 30 meters. How fast will it be going at the bottom? Okay, so what we have to make sure we realize is that free fall is going to mean that the acceleration is due to gravity, so we can just write G, and that's negative 9.81 meters per second squared. Now, what else do we know? Well, if it was dropped, then our initial velocity is 0. We also know the displacement, it's vertical this time, is 30 meters. So we're looking for the final velocity. Okay, let's get to it. VF squared equals VI squared plus 2A, let's put G, delta Y. Again, why did I choose that formula? Because the 4 values that were either given or desired are in it, right? So it makes sense. I don't know what VF squared is. So this one ends up being exactly the same as number 5. Do you see that? It's exactly the same because they gave us an acceleration. We know the acceleration of gravity. And then they gave us a displacement, right? We were given the displacement here. And the fact that both of them started at rest. So start at rest, it's going to go away. I have 2 times negative 9.81 times delta Y. So what do I need to do here? Since this is VF squared, this entire right side should be positive. The only way it's going to work out that way is if I understand displacement as the change in position from start to finish, which would be negative 30 meters in this problem, dropping 30 meters, correct? So we'll get our calculator out. We'll start typing in 2 times 9.81 times 30. Why did I not include the negatives? They don't make a difference. Not in this problem. So we get VF squared equals 588.6. Similar to the last problem, we're gonna have to take the square root of both sides to get our VF value. Square root of the answer, hopefully you guys are familiar with the answer button right there. 24.3 meters per second. So it's going pretty fast, pretty fast. Okay, 4 to go. A rock is dropped. So another free fall problem. A rock dropped. So again, what does that mean? We understand that the initial velocity is going to be 0. The acceleration is due to gravity, so that's negative 9.81 meters per second squared. And they want to know how tall the cliff is if it takes 3.5 seconds. So this problem is different from the previous two because it includes time, which means we're going to probably have to use time. That means we're not going to be able to use the same equation as the last, 3 problems. We're going to have to use this one. yi plus vit plus 1/2. You could put at squared, but I'm going to go ahead and put gt squared because we know we're going to use acceleration due to gravity. So, a couple different ways. We talked about this in class, right? Where I was like, well, if you use this one, then this would be the height of the cliff, and this will be the negative version of that, right? You wouldn't say the cliff is negative 38 feet tall, but it really just depends on, how you're thinking about it. We talked about, sketching a graph, so it's going to do this. This is its height over time. So either way you look at it, this value yi is what corresponds. This is the y-intercept, if you want to take it to math class. So nonetheless, I better finish up. I'm rambling at this point. Knowing this, right, this is going to make it kind of difficult because we don't know what the displacement is and we don't know what the initial height is. So what I'm going to do is eliminate this and pretend like this is the starting point, and so my displacement, if I say this is like 0, the displacement becomes a negative value, and we'll just appropriate that to represent the height of the cliff. So I have delta y, which I don't know, equals VIT. Wait, it was dropped. Don't worry about that. 1/2 negative 9.81, and then the t squared, 3.5 squared. Now make sure you see that's going to give us a negative answer, right? So 9.81 times 1/2 times 3.5 times 3.5. Negative, so delta y equals negative 60.1 meters. Meaning the cliff is 60.1 meters tall. Okay? The parachute free fall, a parachutist free falls for 5 seconds. What's their velocity at 5 seconds, right? When they open it, supposedly. So, exact same, are very similar to the problem. Really the same thing, right? Because they free fall. We know the initial velocity is 0. We know the time value is 5 seconds. We know the acceleration, which is gravity, is due to negative 9.81 meters per second squared. So what we're looking at, instead of how far did they fall, is how fast are they going? So this will actually use the simpler formula, VI plus A delta T. So if we appropriate it for us, VF equals, it was dropped, so we'll get rid of the VI. And then we have GT, so that'd be negative 9.81 times 5. So for our final velocity, we get negative 49.1 meters per second. Why is it negative? Because they're going down. Okay, a ball is thrown up with an initial velocity of 3.9 meters per second. How high does it go? So this is going to be one that, it's really helpful to draw. Make sure you realize that they didn't tell us an initial height, so we're going to ignore that. And what we want to make sure we see is the velocity up here at the vertex is 0. So if it starts, the initial velocity was 3.9, then the final velocity is going to be negative 3.9. Hopefully you remember that from our discussion in class. Equal and opposite reaction, right? So what we're going to do is first find the time it takes to reach a velocity of 0, okay? That's going to correspond with the time occurring at the maximum height, right? right? Or, we could just kind of skip. Let's see. Does this equation work for us? Plus 2a delta. I'm going to use delta y in this problem. I'm going to use delta y because it's a vertical motion. So you think about it, this should be g because we're talking about a free fall or a projectile. And what we're doing here is saying, hey, what if I say this was the end of the event for the purpose of our analysis? Right? I just want to stop here and say that's the final velocity. It would be 0. The initial velocity would be 3.9. We have g, it's negative 9.81, and then that leaves us to solve for y. So we could have went through and found out what the time value was using this formula, VI plus G delta T, right? You think you can solve for T there, and that's going to tell us exactly how long it's climbing. Of course, remember that we double it to figure out how long it's in the air totally, but they didn't ask for that, so I didn't bother with it. So let's see, 3.9 squared. By the time I move it over here, it's going to be negative 15.21 equals negative 19.62 times delta y. This one really doesn't go that high. So we're going to divide by negative 19.62. So negative divided by negative, it's just going to be positive, right? 19.62. So delta y will equal, not quite 1 meter, huh? 0.78 meters. Wow. 3.9 meters per second. It's not really going to get us that far when the gravity is pulling down so hard. Okay, this last one, we haven't done a lot like this, but a ladder height is 12 feet and a ball is thrown up from that height. So what I'm going to do, we're going to take note. We're going to say, okay, the initial height is 12. It hits the ground after 4.2 seconds. So the repercussions of this having an initial height are that we are not able to use symmetry in the same way that we have before. The ball is actually going to be leaving from 12 feet here. So 12 feet, and then it's going to come back down. There is symmetry present, but it's here. So whenever it comes back down to the same level. Remember, equal and opposite vertical distances, right? So whatever the initial velocity was here, it's going to be equal to that here, just negative. And then this last little bit here, the ball's going to gain more velocity than it had ever possessed before, just in the negative direction. So the greatest speeds will occur here in the pink section. But how do we find those? So what we want to think about is this equation's got to use time. And so that doesn't really leave me with a lot of options because I don't know the final or initial velocities. So what we've got to go with, we've got delta y equals yi plus vit plus 1/2 gt squared. Now let's make sure we understand everything we have. We know the initial height is 12. We don't know vit, but we do know t, 4.2. And 1/2 times negative 9.8 t squared. Oh, wait, that's right. 9.81, and that was 4.2. So that's a squared. Do we know the displacement? It's a very tricky question here. The answer is yes, because the ball started here and ends up there, which is exactly 12 feet lower than it started, right? So the ball covers a displacement of negative 12 feet over the 4.2 second interval. So very tricky question there. So what we're going to do is just work it from there. We'll subtract 12 from both sides. So I've got negative 24 equals 4.2 VI. Let's see, what are we going to get here? Something negative, right? Minus, do a little calculating here. 1/2 times 9.81 times 4.2 times 4.2. And of course, that's going to be negative. That's why I wrote the subtraction. 86.5. And of course, we'll add that to both sides. 86.5, 86.5. So I'm running out of space here. Let's see if I can get a little more room here. So what I've got then, so let's say minus 24. Oops. So I've got 62.5 feet equal to 4.2 VI. Of course, now it's really easy. We're just going to divide both sides by 4.2. We'll get 14.9 feet per second equals VI. Okay, so this would be much easier with Desmos because then we can kind of show and check our answers. But I'm not going to require you. We're not going to use that on our test, so I don't want to give you a crutch. All right, guys, good luck. I'll see you tomorrow.